Good morning, everyone. Welcome to Campus Friday. Today we'll have our speaker, Professor Laxague. Professor Laxague is an assistant professor from University of New Hampshire. He obtained his Bachelor of Science in 2011 and PhD in 2016, both from University of Miami. He worked under the supervision of Dr. Brian House here, who's also my advisor in Sustain Lab. And before joining the University of New Hampshire, Dr. Laxague worked in Lamont Earth Observatory as a postdoc researcher in New York. Now he's joining us for the conference seminar. His research interest lies in surface wave mediation of air-sea momentum flux, as the title has explained, and he's particularly interested in the physical mechanism of how the interaction between air and the water will be. And to solve such problem, we'll be able to look for the best engineering solution for the in-situ observation. Today, our talk will be surface wave mediation of air-sea momentum flux. So, Dr. Laxague, welcome back to Rasmus, and please take the stage.
Thank you very much.
Welcome.
Thank you, Payson, for that introduction. As you mentioned, my name is Nathan Laxague. I've been away from Miami for about 5 years, but it's very good to be back and to be speaking in front of you. As Payson mentioned, and as you can read on the screen, the title of the seminar is Surface Wave Mediation of Air-Sea Momentum Flux. So I'm going to talk to you about air-sea interaction somewhat broadly, but then zoom into a particular flavor of air-sea momentum flux, and then how waves can mediate that exchange between the atmosphere and the ocean. So what I'd like to do is separate the seminar into 3 distinct sections. The first one will be a background with more than a little theory maybe, but just enough to get things going. Second, my observational approach. And third, an illustrative case study. So I don't expect this seminar will be exhaustive. I'm going to zoom in on a narrow range of scales of motion and leave out a lot of the really important physical processes. And I'll probably even be a little bit light on my own results than beyond what is standard, but my hope is that everyone here leaves with something, perhaps a deeper appreciation for the role that surface waves play in air-sea interaction. Okay, to start things off, the background. You may have seen this type of diagram before. I believe it's called a Stommel diagram. But what I'm doing is displaying the typical ranges for a number of physical processes in the atmosphere and ocean. On the horizontal axis, that's the horizontal spatial scale, and the vertical axis is the temporal scale. And from the lower left-hand corner up to the upper right-hand corner, you can see surface capillary waves, that is waves that are restored to equilibrium by surface tension, surface wave breaking, which kind of straddles the surface capillary and gravity waves. Gravity waves, of course, are the ones that are restored to equilibrium primarily by gravity. Langmuir turbulence, the interaction between wind stress and wave-induced drift. Inertial, internal, and solitary waves, sub-mesoscale phenomena, and then sea breeze. And at the very top, I put 3-letter codes: DNS, direct numerical simulation, LES, large eddy simulation, and GCMs, your larger scale models. So for the people in the audience who are watching remotely who take a computational approach, that might provide a little bit of a guidance for most people actually here at Rosenstiel and really elsewhere in earth sciences, geophysical dynamics. They probably live beyond the upper right-hand corner of this in the climate scale or the global scale. So they might think of air-sea interaction like this, where you have basin scale or synoptic scale interaction between the air and the sea. But the flavor that I'm going to zoom into today is actually on the small scale, what I consider the small scale. So surface gravity and capillary waves, turbulence in the upper ocean and lower atmosphere boundary layers. I say coupled boundary layers because they really are truly coupled. I always tell people that my understanding of geophysical fluid dynamics ends once Coriolis becomes important. And if I have any students from my Waves and Tides course at UNH, I'm joking. Obviously, I'm a reputable source on this subject. Okay, so air-sea flux. Let's get right into it. In broad physical terms, you can think of a flux as the passage of some quantity through some surface, represented by, if your quantity of interest is momentum, you can divide the momentum, take the rate of change of momentum, and have it pass through a particular area, and that gives you units of stress, or force per unit area. So if you're interested in describing air-sea momentum flux, you can think of that as the vertical transport of forward momentum, or the shear stress applied to the interface by an adjacent fluid. And in practical terms, the fluid doing the forcing is often, but not always, the atmosphere. And in low wind conditions, there are these famous cases of the ocean pushing on the atmosphere. So upward momentum flux, but for the most part, we'll be talking about the wind blowing over the water and the physical system evolving from there. Okay, so the air sea momentum flux, we can break this down, or we can represent this in the following manner with the fluid density times something called the friction velocity squared, and we can decompose the stress into viscous, tangential, and wave form stress components. So the tau nu and the tau w, those are the viscous, tangential, and the wave form stress. Okay, why is it important to break those apart? Well, because they vary as a function of wind forcing. There's a cursor floating in my plot. Oh, I don't know that it's mine because I'm moving mine around. Oh, that's weird. Phantom cursor. Okay, apologies for that. So the parameterization from Mueller and Verone in 2009, they offered a means for describing the variation of this decomposition with increasing wind speed. So viscous tangential stress dominates at low levels of wind forcing, or low levels of wind speed, I should say. And the waveform stress increases with increasing wind speed. So the astute mathematicians in the audience may notice that those two don't add up to one, and I am neglecting the stress associated with airflow separation due to breaking surface waves. This is a very important part of the picture, especially for high levels of wind forcing, but I'm going to neglect it for today because you have to leave something for next time, and it really would take a lot more time to get into the dynamics of wave breaking. Okay, so how do we characterize these stress components? Let's start with a very, very simple picture of the air-water interface. Just a line, the most simple formulation of it. Imagine that you have these two fluids, they're separated by this hard interface, 3 order of magnitude difference in the fluid density, and you begin to blow wind over the interface. So the fluid on the top starts to move relative to the fluid on the bottom. So boundary layers begin to form on either side of the air-water interface. And the velocity profile is continuous across this interface in this simple setup. Out towards, z goes to infinity, you get this free stream velocity, but then at the interface, you have continuity across it. So let's zoom into the water side. In the uppermost portion of the velocity profile, we can actually pick out 2 distinct portions. In the uppermost layer, you have the viscous sublayer, where viscosity damps turbulent motions, and we expect, from Newton's law of viscosity, which is written right there, that we should have a linear velocity profile. And then below that, in this inertial sublayer, we have a regime where we expect the velocity to decay logarithmically. And you may find that form familiar if you do atmospheric or boundary layer meteorology, something like that, where you're looking at logarithmic decay or logarithmic increase of velocity with distance from a hard surface. The little symbols there, U star, water that's our friction velocity in the water, kappa is the von Karman constant, and then d sub w is the thickness of the viscous sublayer, and z naught w, that's the friction velocity in the water. Okay, and the reason I'm showing this is because you can obtain the viscous tangential stress by determining, let's say you're able to measure the velocity profile in the inertial sublayer, you can perform a logarithmic fit and obtain the water side friction velocity, and then from that obtain the viscous tangential stress. I say that because obtaining it by measuring the current profile in the viscous sublayer is tremendously difficult, and I won't go too much more into that right now. Okay, the wave stress, the other part of this puzzle. So wave stress can be computed, and I apologize, integrals are coming. The wave stress may be computed as the integral over all wave number, frequency, and direction of this integrand, which has rho w, that's the density of water, g, that's the acceleration due to gravity. You have this Sn over c, which is a wind input source function, divided by the wave celerity, or the wave speed. And then that f, that function f of k omega theta, that is your directional wave number frequency elevation spectrum. So if you were to make a measurement of the spatiotemporal variation of the wave field and compute a Fourier transform, you would get that. Okay, so Sn, that's really the mystery piece in this puzzle. There's a bunch of different ways to compute that. People spend their entire careers coming up with ways of modeling this. Mark Donlin spent a large portion of his career on this very problem, and a lot of that work formed the basis of his wave model. So I'm going to choose Planck's formulation, Bill Planck's formulation from 1982. It starts with the Miles style. So I'm not going to get too deep into this, but there are 2 early formulations of surface wave growth. If you take the one from the so-called Miles formulation, you have a wind input source function that varies like friction velocity. That's what I'm going to take, and you'll see why in a couple seconds. Because if I substitute that into my first integral, I get this thing, which if I use linear wave theory in deep water, I can obtain a simplified version, which I'm skipping through this very fast, but the idea is what pops out on the end is just a single integral. evaluated over all frequency. And it turns out that that is the mean square slope. So I'm integrating the slope spectrum in frequency space and obtaining the surface slope variance. So this tells us that the wave stress is linearly proportional to the surface slope variance, or the mean square slope. This is under the special case that we can describe this wind input source function, and it takes the form that Plant outlined in 1982. Okay. The reason I'm making this step making this simplification is because it gives us a single piece of information we can obtain to get insight into how the waves are growing, how the waves are taking up momentum from the atmospheric forcing. Okay, so we want to measure the surface slope variance. We can just do that a couple different ways. We can make measurements of the surface slope and take the variance, like you would in the statistics course. You can also compute it as an integral moment, as I'm doing. I guess people who are virtual can't see, but I'm pointing my laser pointer at that lower left-hand corner integral. You can compute an integral moment of the surface slope spectrum and obtain the mean square slope that way. The nice thing about doing it that way is you can decompose your mean square slope by scale, and I'll show you what I mean by that. This right here is the cumulative density function, or several cumulative density functions for surface slope variance at 7 different wind speeds. And as I'll get into later, it's difficult to obtain the spectrum, or the spectra that produce these curves. So I'm using a model spectrum that was produced by Elfo Haley and co-authors. Pretty seminal, famous paper from 1997. But you can see that there is scale separation that varies with wind forcing. So at low levels of wind speed, most of your slope variance comes from a pretty tight range of scales. At higher levels of wind speed, you get a broader range of contributions to the surface slope variance. For illustrative purposes, I'm going to introduce something called the bond number. The bond number gives the ratio of gravity to surface tension forces, and you can get it right from the gravity capillary dispersion relation by basically dividing the gravity part of the dispersion relation by the capillary part. And what you see is, evaluating it gives you these 3 different regimes in the spectrum. So for a bond number of a bond number of greater than 1, you would call those gravity waves. For a bond number on the order of 1, you would call those gravity capillary waves. And then a bond number of less than 0.1, you might call those capillary waves. I think I bungled that, but essentially it's not a clean cut. There are scales where gravity and capillarity are both important. We call those gravity capillary waves or capillary gravity waves. And it turns out that you really need to obtain, if you really want to get a good handle on how this quantity varies with wind forcing, you have to characterize surface waves that are of scale 10 meters to 1 centimeter, which is a very tall order. And we'll get into why in a couple slides. Okay, so one of the challenges behind this is that our historical measurements, or typical measurements of surface waves, happen for scales much larger than 1 meter. So as an example, we expect a particular spectral behavior in the so-called equilibrium range, where there's a local balance between wind input, nonlinear interaction, and dissipation due to braking. And then another spectral behavior in the saturation range, where there is a balance between wind input and dissipation only. But then if I tell you that small scales are very important for air sea momentum flux, then we really want to know what happens as we get to smaller and smaller scales where capillarity becomes important. And that brings us to part 2. So we're done with the didactic classroom experience, and we're going to get into a little bit more of some practical applications. Okay, so one of the tried and true tools that we have for studying surface wave behavior is the buoy. It floats and bobs on the ocean surface, and it telemeters, or it stores its position and attitude, so it's angled with respect to the free surface. And you can imagine that you would see a recorded time series of vertical surface displacement. This is actually from a spotter buoy, the buoy that I showed on the previous slide. And these measurements were made off the coast of New Hampshire. But there are a few shortcomings to this approach. It's a point measurement, so it records the temporal variation of the wave field at a particular point. And I say point, but depending on the buoy construction, that point could be 40 centimeters, like a spotter buoy or a smaller buoy, or 3 meters in diameter. Your standard discus buoys are 2 or 3 meters. And that obscures, maybe in some cases completely obscures, the waves that we're interested in. I apologize about the frame rate of that. In the era of Zoom, we don't get the crisp, buttery videos that you get in person. So just imagine if you're not seeing a flip book. Okay, so this is the part of the seminar where I try to convince you that the work that I'm doing is indispensable, And I'm bringing a whole new formulation to the problem that's going to change how we think about it. So one of the approaches that I've been using, and also in collaboration with Dr. House, has been to take advantage of the fact that the physical properties of light change upon reflection from the air-water interface. So this is what that looks like. You have a free surface, you have a bundle of light come in, and you get a reflected bundle of light. Okay, so those two column vectors represent the Stokes vectors for incident and reflected light, respectively. So this is what they look like when you peel them apart. The Stokes vector gives us the polarization state of the light. So we're not going to worry about the RC and LC components that make up S3. Those are circular right-handed and left-handed polarization. Extremely rare in nature. Their principal use, I think, is in making 3D movie theaters work, because you don't want to have red and blue lenses. You want to have one projector that's giving you right-hand circularly polarized light, and the other projector that's giving you left hand, and you don't have to vary the color, so you can have true color images in the 3D movie theater. I think that's neat. It has nothing to do with my research, but that's where S3 comes from. Okay, so from a single camera, this is a polar sense detector that was produced by Sony a couple of years ago. It's a really amazing piece of machinery. It's almost a miracle that it exists. But from a single camera, we can obtain the first three Stokes parameters. So those are S0, S1, and S2. S0 is what you would see if you just pointed a boring black and white camera at the ocean surface. You can see, if you really squint, it looks like my fake background, like a chalkboard. You have this gray surface, and then these little bright patches, those are foam on the water surface. With S1 and S2, though, you're taking into account contributions that are not just the total intensity, you're looking at the actual orientation of the free surface. So from those three pieces of information, we get the angle of incidence, which I'm using the Greek letter theta to denote, and the polarization orientation angle, which is, I'm using phi. And this technique was first, use of polarimetry to obtain topography has been around for decades in the computer vision world, but it was first brought into the study of ocean hydrodynamics and fluid mechanics by Christopher Zappa and colleagues. And the first paper was in 2008. There was an update to the technique in 2012. And from that, you can compute the surface normal vector field. So the vector normal to the surface at each pixel can be explicitly described as these trigonometric functions of your phi and theta angles. And then you can use those surface normal vectors to obtain the surface slope field. And these are the slope defined in the Cartesian coordinate system x and y. So you can think of the left handle as being the cross-look slope, and the right handle as being the along-look slope. So if we do this 30 frames per second, because we have a camera that can give us this information 30 times per second, we get something that looks like this. So these are images taken in short succession, which give us a fully spatiotemporal representation of the topography of the surface wave field. So you can integrate the slope field in space to obtain the surface elevation field. I don't usually use this product for anything more than presentation. If the frame rate were higher, it would be a little bit more impressive. It looks great on my screen. So just imagine that you see this crisp, undulating free surface, characterizing surface wave scales down to centimeters, all the way up to 2 meters in this image. Okay. So to sum up, we take the measurements of the surface slope field, which can be represented as the gradient of this elevation field eta. We compute a fast Fourier transform, or a 3D fast Fourier transform, and we obtain this wave number frequency spectrum, wave number frequency slope spectrum. And that gives us the information about how the surface slope varies in wave number, or spatial scale, frequency, or temporal scale, direction, and if you have a short enough period of analysis, time. So you can look at the temporal variation in these quantities. So a number of these measurements were made off the research platform Flip in the Santa Barbara Channel as part of the 2008 radio campaign. So I won't dwell on the details of making this type of measurement on a moving platform, but as you can see from this video, even the relatively stable Flip moves enough to make real-time motion correction an absolute necessity as the platform gently sways. Again, this is, I mentioned Zappa's 2012 paper where he described the measurements being made, and then 2 follow-up papers where we discussed the variation of the surface wave number spectrum with wind forcing and the consequences for current in the uppermost centimeters of the water column. Okay, so I know there's no axis labels. It's major cardinal sin, no axis labels on that right video. The major tick marks are 50 centimeters. So this is a very, very small patch on the water surface, less than a meter by a meter. Okay, so with that capability in hand, let's go back to the problem that I described earlier. How does the surface slope wave spectrum vary once we get out to scales where capillarity becomes important? So in the measurements that were made in the Santa Barbara Channel in 2008, but then written up in a paper 10 years later, we found really substantial variation with wind speed at those scales. And a couple things jump out, but I'll note one in particular. The wind speed dependent development of the spectral peak in the gravity capillary regime, so out here, really becomes quite prominent. And beyond that, you get this substantial decay. So you do see a well-defined equilibrium range, maybe a saturation range, but then as soon as your bond number, I guess too many animations in one slide. As soon as your bond number reaches the point where you may have capillarity being important in your dynamical problem, you start to get this separation of the spectral energy density with scale. And to me, that indicates that the behavior of the surface wave spectrum at scales where capillarity is a significant part of the picture, that's important for air-sea momentum flux. We've indicated that the surface slope variance is a key determinant of the surface wave stress, and the determinant of that mean square slope varies substantially as you get out to these small scales. It's difficult to imagine coming up with an accurate representation of this and not including any of the dynamics that occur, or any of the spectral properties that occur for wave numbers that are smaller than 100 meters, say. Okay, so I'm going to get now into a case study. So these are mostly results that were contained in the paper that came out 2 years ago, namely the impact of rain on surface waves and the consequence for air-sea momentum flux. Okay, so we're going to go in a slightly different direction. We're going to talk about what some other people worked on, and then tell you how my work and my colleagues' work have impacted this field a little bit. Okay, so the classic observations of Simpless and Thorpe from 1989, my birth year, the authors quantified how the surface wave spectrum changes under the impingement of rain. And this is an artificial rain field with a bunch of hypodermic needles, and they could adjust the rain rate and look at how, when you blow wind over the water, how the surface wave field reacts to these, to the flattening effect of the surface waves. I say flattening effect, I'm stealing my own thunder, because Harrison and Rowan in 2017 published this really nice paper that showed how for different rain rates and different levels of wind speed, you can either have a complete flattening, a complete suppression of the surface wave field, or just a minor variation. So there is a dependence on the rain rate, and there's a dependence on the wind speed. So let's move away from these curved plots and move into something a bit more tangible. On the left-hand side, I have a slope field, or a cross-look slope field, in the absence of rain, and on the right, a cross-look slope field in the presence of rain. I've taken two little slices out of each of those, or one little slice out of each of those, and shown the surface elevation. So I've integrated the slope field, and right beneath that is the surface elevation variation with space. You can see that when there's no rain, you have this nice clean undulation. In the presence of rain, you have these small dimples, these little rivets, impact craters, and these ripples that propagate radially outwards. Okay. So what happens as a result of this change beyond the water surface just looking different? Well, Poon and co-authors in 1992, they reported an increase in near-surface current speed following this rain-induced suppression of the surface gravity waves. And then later, Schlussel and others, I think including Alex Sloviev was on that paper, friend of the community, described the consequence of this as being a shift in the partition between waveform stress and viscous tangential stress. The idea being you suppress your larger scales of surface waves, you have the same level of wind forcing, so the balance shifts from a reduction in surface wave stress is compensated by an increase in surface viscous tangential stress. That was their hypothesis. Okay, so in order to test, I shouldn't say test this hypothesis because we already knew it was going to happen, but in order to evaluate this claim, I guess we should measure the wave height on or slope in this case on meter to millimeter length scale, so we can really get a good handle on the wave stress and then see, okay, what is the corresponding effect for the tangential stress or the current profile. Okay, so to answer this question, I shouldn't say this. The cruise was not intended to answer this question. It was an opportunistic event where we encountered a single impulsive wind and rain event in the course of this cruise in 2016. And from that, we were able to use those data to look at the interaction of wind and rain with the wave and current field. Okay, so this is the RV Falcor. Right off this O2 deck, we had a polarimetric camera. That's an exaggerated grazing angle. But we had a polarimetric camera looking at the water surface, and we measured the wind speed from the foremast. And so on this particular fateful day in October of 2016, we had a pretty calm day. It was 4 meters per second wind, when all of a sudden the wind speed almost tripled, and this really spectacular rain event came through. No stranger to the people this is not strange to the people in the audience, but 100 millimeters an hour is, that's a lot of rain. That would cause some flooding if it happened over land. Okay, so I'd like to draw your attention to the rapid increase in wind speed when this front arrives that is coupled with a dramatic increase in rain rate from 0 to 100 millimeters an hour, followed by basically a pause in the rain while the wind speed persists. So I'm going to show you what the surface looked like when the first raindrops came, and then show you what happens as the rain rate evolved. So occasional raindrops, which are hitting the surface at this point, don't even register on the tipping bucket measurement device. On the top of the ship, there was a little tipping bucket. When it would fill up with water, the center of mass would change beyond some fulcrum, and it would tip over. And then this little logger would count each time the bucket tipped. That gives you a volume per hour. You compute the surface area. Okay, now you know the rain rate in millimeters per hour. So you can imagine that these tiny, tiny little raindrops, which register on our polarimetric camera, our polarimetric slope measurements, those aren't even registered with the tipping bucket scale. Okay, so if we look at the surface slope variance over this time period, we can see that there's a maybe slight suppression in the longer surface gravity waves and a really dramatic enhancement of the centimeter scale waves. So what I'm doing here is I'm computing the percent change in mean square slope, surface slope variance, but I'm not just adding up all the slopes, or adding up all the slopes squared. What I'm doing is integrating the surface slope spectrum over particular ranges. So I don't have these as wave number ranges, but really what you do is you integrate the slope spectrum over K1 to K2, where you define those as, this is a certain bond number, that's a certain bond number. You can see that the short gravity waves, this would be 5.6 millimeters to 615 millimeters, a little bit weird to your eyes. To think of a 5.6 centimeter wave as being a gravity wave, but if you look at the bond number, its primary restoring force is indeed gravity. It's not short enough to really be primarily restored to equilibrium by capillarity. Okay, so what happens when we look at the broader changes in the time series, not just this initial onset? You can see I've got these images every 5 minutes, and then one that I've selected towards the end during this little brief pause in the rain. You can see the initial slope field on the far left at UTC of 0300. We have a little bit of raindrops that are dimpling the free surface, and then at 305, we have a complete disruption of the surface wave field. It's really difficult to say whether or not there's any waves there. What we have, if you were to look at the video or you look at the spectrum, what you would be able to see is, in fact, that there are longer waves there at 305. That would be the green curve. There are longer waves. They're just suppressed. And really the prominent feature, an order of magnitude more prominent, in fact, are the centimeter scale ring waves. And in that case, it's probably not just ring waves. It's like I was saying, impact craters, ejection droplets, and objects that make Fourier analysis very, very challenging. Okay. And then really what I think is quite interesting is what's happening in the far right panel, where the wind speed is still elevated, about double what it was before the rain event came, but you have almost no rain. Maybe an occasional drop here and there. The tipping bucket is still recording something. That could be some residual water, some oscillation, whatever. But what we see is that the short gravity capillary waves, the ring waves and such, those have diminished basically to their pre-rain state. But we have this recovery of the surface gravity wave energy. Essentially, as we'll show in a couple slides, the wave field has recovered due to wind forcing. Okay, and you can see that I've identified those as being the gravity waves. Okay, so this right here is the time series of wind speed and rain, and then on the lower panel we have the saturation spectrogram. So the spectrogram is here to show you the variation of the surface wave spectrum in time. And I've created a couple, I've differentiated this in time, and I've computed the surface wave growth rate. So if you differentiate the spectrum in time, and you divide by the spectrum itself, you get a sort of normalized growth rate. I didn't talk about the Miles growth model, but essentially you would expect that you get, it's called a growth rate because the change in the wave field is proportional to the energy of the wave field itself. It's exponential growth rate. So this parameter beta tells you the strength of that exponential growth. And I'd like to partition this by bond number. Right here we have bond number of greater than 10. I'm calling those gravity waves. This Goldilocks zone where the bond number is of order 1, that would be gravity capillary waves, and I've partitioned those into ones that are ever so slightly closer to gravity and the ones that are ever so slightly closer to capillarity, and then the pure capillary waves, which we resolve some of, but not really enough to say too much about. Okay, so I think the most interesting thing that's happening in this figure is the change in the spectrogram during this pause in the rain event, where there is a suppression, if you like, but really a pause of injection of this momentum at the surface gravity capillary scale, because the rain is no longer falling to the degree that it was, and this lobe of growth, where you have waves that are really growing and increasing in length scale, as you might expect under surface wind forcing. Okay, so the main thrust of this paper, yes, it was on this work. Yes, it was on how the surface wave field responds to the forcing, but really it was also about how the underlying flow responds. And then from that, what can we tell from the response of the underlying flow to the air sea momentum flux? So let's look at this time series. Again, I have what I showed before, but over the entire measurement period, this percent change in mean square slope, where the violet curve, that's the darker one, might be difficult to see in the projector, but the violet curve are the waves that are longer than 1 meter. And the way that we got those was by actually computing a short time scale variance, the old-fashioned way. We've got maybe 10 centimeters, and we'll compute, 10 seconds, we'll compute a local, or a temporal variance. And then for the teal curve, well, we're going to compute our mean square slope the integral way. We're going to integrate our slope spectrum. And what we find is that the near surface current, and here I've represented the near surface current, multiplied by 100 and divided by the 10 meter wind speed, U10, it increases dramatically when the, right around the period when you have increase in rain rate. Okay, so the idea here is that you have an increase in the near surface current speed when the wind forcing is very high, but also the rain rate is very high. And then the wind forcing stays pretty high. The wind speed is 8 meters per second, but the rain subsides. And at that point, you get a subsidence of the near surface current back to its pre-rain levels. You would expect, okay, the near surface current, which just scales like the wind speed. It's 3% of U10, fine. In this particular case study, we actually found that it tracks the presence of the rain. And so there's a period of acceleration and then a period of deceleration. And I highlight this, you don't really want to build your understanding of the world on a 20-minute single measurement, but I think this type of measurement highlights how important it is to capture these short time-scale transient phenomena. Because if you were just taking a 20-minute average, you'd completely miss this. You'd probably get some small elevation in near surface current speed. You'd have no way of tying it to this individual impulsive event. And we have a tipping bucket gauge that records every 1 minute. And we have a polarimetric camera that was giving us measurements 60 times a second. But you could have easily said, well, this is a single acquisition. We'll compute a single mean rain rate. The mean rain rate is probably 20 millimeters an hour. It wouldn't look like much. But if you look at the radar, you see this tremendous destruction of the surface wave field. In any meaningful sense. Okay, so the takeaway there, the big bullet point, wind-induced currents, in this particular case, they track changes in the surface gravity wave slope variance. So you can see this little dip right here, this little dip right here, which coincides with this acceleration of the near surface flow. Okay, so that's enough for what I've been working on. That probably looked terrible. It looked so good on my screen. Okay, well, it didn't look so good. It looked better than terrible. Okay, so this is the irons that are in the fire, the current and near future endeavors. And so the iron that's currently in the fire is looking again at this data set that was collected in 2016 on the Falcor, but going a little bit beyond a single case study. The video, and this is with my collaborator, Christopher Zappa, at Columbia University, Monterey Earth Observatory, and my PhD student, Shantanu Somia, who's probably watching. So the left panel is the skin temperature as observed by a cooled infrared camera. We take those images, we put them into a PIV algorithm, and we obtain the surface velocity field. Well, as you probably learned from Dr. Rohmeiser's class, we don't want to compute turbulence statistics on a data set that has a bunch of wave motions in them, because wave motions are to first order irrotational. So I'm computing the rotation, or the curl, of that vector field, and then in the style of Sutherland and Melville, I will compute the turbulent kinetic energy dissipation rate from that vorticity spectrum. So the color that's underlying this velocity field, that is the vertical component of the vorticity at the surface. We also have, obviously, the slope measurements that I was describing earlier. The wrinkle with this particular data set is it was in the southern equatorial Pacific. Some measurements were made near the coastline of Australia, some were made in the deep ocean of the Pacific. But in all of the cases, there were cyanobacteria. There were these biogenic ocean slicks. Biogenic slicks, they change or all surface slicks, they change the surface tension, that changes the surface wave field. And there are lots of cases of this really dramatic suppression of the surface wave field for constant levels of wind forcing. So if this work had been more mature today, you probably would have seen more of this. But as it stands, if you're going to the American Meteorological Society meeting in January, my student Chandra will be presenting a poster on this. So hopefully we'll have a lot more to present at that time. Okay, another iron in the fire was to use measurements that were made a couple years ago in collaboration with my colleague, Dr. Zappa at Lamont Doherty Earth Observatory, where we measured the wind stress from the ACIT tower, the air sea interaction tower, just south of Martha's Vineyard, and a mounted polarimetric camera. The nice thing about this, you don't really have to worry too much about motion correction, and you can just collect during daylight hours as much as you like on an automated schedule, and you build up a really nice size of data, so you have good statistical power, which you may have noticed those curves from earlier on Flip. There were 16 spectra. It's difficult to extrapolate too much from that, but those are the only measurements of their type, and so we do what we can. But hopefully with the analysis of this data set, we will have a much more robust, well-defined data set that we can really tell some important physical things about the air-sea interface. Okay, and then the last iron in the fire, it's the iron that's being prepped to go in the fire. This is an airborne platform that has been constructed. It's in my laboratory right now. Two other students in my group are working on this, Goksu, Devarchi, and Berg. They are helping me out with a lot of the testing and validation. For a lot of reasons, it's very handy to be able to make the measurements that I've been describing from a flexible airborne platform. There are challenges that are associated with that, but with the right hardware and the right testing and validation, you can actually make a very clean, crisp measurement, have a lot of flexibility to deploy it in a range of conditions, vary your altitude, vary your heading. So I'm very excited about the work that is to be done here. Nothing to show yet, obviously, but I hope by Ocean Sciences 2024, I'll have at least something beyond a stock video that I got from the drone manufacturer. Okay, so in sum, taking a while. The exchange of momentum between the atmosphere and the ocean, it generates surface waves. That's no great revelation. They grow, steepen, and they break. Wonderful. Okay, so these processes themselves actually do modulate the air-sea momentum flux. There are feedbacks that contribute to the exchange of momentum between the atmosphere and the ocean. And if we characterize these physical processes, if we want to characterize the physical processes, we really want to measure a large range of scales, and especially a range of scales that are not typically measured routinely by buoys and fixed wave measurement systems. Okay, and I think that I've presented at least a little bit of evidence that with the right technical capabilities, we can make these measurements, but there's a lot more that's left to be done. So I've shown a couple case studies and niche observations, but my hope is that in the next 5 to 10 years, we'll have a really large body of observational data that can be used to inform wave models and things of that nature. And with that, I will say thank you very much for your time. And if you'd like more information on the work that I've been describing and what myself and my group members are working on, I put our website down there at the bottom. It's unh-castle.github.io. The Castle is coupled air-sea surface layers laboratory. So yes, thank you very much for your time and attention. That's it.
Yeah, thank you very much. Very nice presentation. Questions from the room? Yes, Lisa, and I would recommend that you come here and speak in front of the camera so the Zoom people can can hear what you are asking and can see you. If that's not.
And they can just repeat it.
I'd be happy to repeat it.
Well, I can do it. Yeah. Okay. Okay.
Sorry, being lazy. But it's a dumb question, so I don't want to go up there. Nathan, how did you measure the current? So in that 5 minutes of data that you were showing a lot of, and I'm no expert in this interaction, but I was just curious of how you measured the current that you said responded to rainfall.
Yes, great question. That seems like the most important detail to mention. I completely glossed over it. As you can imagine, if you have an acoustic current meter, it's probably going to miss those really short, impulsive events. We use the Doppler shift in the surface wave field. So we were able to compute these short window fast Fourier transforms in wave number frequency spectra, and then find the dispersion curve. So basically how the surface waves were shifted in frequency, and then use that to infer the near surface current. So if the waves were moving a little bit faster than you would expect, we'd say that's due to current. And the way that we accounted for nonlinearities in the spectrum was we didn't say, okay, we're going to match it to the dispersion relation, which is usually a mixed bag. We said, okay, what's the difference in the wave speed between upwind traveling waves and downwind traveling waves? And you can do that with these really short waves because once you get to centimeter scale, decimeter scales, you do have a lot of wave energy that propagates upwind. It's just not as obvious. But if you have a spectrum, you can observe that. This is work that I did here at Miami with Dr. House, but worked on a lot more as a postdoc, and I feel pretty confident in the technique. Obviously, it needs more refinement. I didn't show any variation with depth in that figure. I just said I just took an average over all wave numbers. But yes, that's it.
So there isn't kind of a circular argument with that, because you're using some of the character of the surface waves to tell you about the current, but then you're saying that the character of the surface waves is changing depending on the wind and the rain.
Yes.
Can you
So
tell them what these are?
Yeah, I'm sorry, I didn't repeat the question. Dr. Beal asked, or made the comment that this could be in fact circular because I'm saying there's a relationship between these two quantities, the near surface current and the kinematics of these free surface waves, but both of these quantities are coming from the same measurement. So could I be confounding? And that's a great point. My argument, or my response to that would be that they are distinct in that I'm looking at the spatiotemporal evolution, the behavior in wavelength frequency space independent from the amplitude. So if the waves are moving a little bit faster, it's not necessarily because they're taller. So the surface slope variance is giving us information about how much energy is in the wave field. You could have a low energy wave field where waves are being moved very quickly by a current, and there would be no reflection. I mean, if you had if you had divergence and curl of the near surface flow, you would get bunching and you would get an increase in surface slope variance that would be tied to the near surface current. But in this case, with just unidirectional flow, I feel comfortable in saying that they are, if not completely independent measurements, I don't think that the confounding is too severe. But we also have an infrared, we also have an infrared camera from which we can get the surface velocity field. Obviously during heavy rain, that kind of goes out the window because the whole atmosphere between the camera and the water surface becomes opaque. But with some filtering, we were able to make some measurements leading up to that point. And maybe if I gave a better version of this talk, I would have shown some of those measurements.
Cool. Thanks for that explanation. I guess if I'm allowed to have one more question. So what depth would you say that current that you extract is at?
Yeah. So the follow-up question was, what depth is the current so the current that I'm showing, I'm calling it near surface current, what depth is that representative of? And that's a great question. It's a little bit of an open question. From simplified theory, you can say, okay, it's 8% of the wavelength or 4% of the wavelength. The wavelength range that we're observing make it so that that is probably an average over the upper 5 centimeters of the water column. There's a couple more sophisticated techniques where you can get a better estimate of it. And the reason I'm not giving a straight answer is because it turns out that it's very easy to obtain the variation of current with wave number given the known current profile. But the inverse problem is, well, it's transcendental. The inverse problem is quite difficult. So if you measure the variation of current with wave number, it's not straightforward at all to get the variation of current with depth. And people like Bjorn Lund, who spent half their career working on doing that, it's not an easy problem, you know? So I guess the best answer I can say is, and a lot of people have just said, you know, I'm just tired of doing this inversion. I'm just going to say, take an average over all these scales and say it's about that. And you know, for our purposes, upper 5 centimeters is probably pretty close to the near surface. I get a little bit weirded out when people make radar measurements and they say it's surface current, not to throw any stones, but if you're talking about an average over the upper 10 meters, you know, it is the near surface current if you're studying, you know, the whole water column, but in coastal regimes, you know, there's a lot of variation that happens in that upper 1 meter. But of course we can always slice that ever thinner. There's always a purist to the left or right, or maybe you can say, well, I'm measuring the true surface current. I think the infrared people went out because they're making measurements in the upper 10 microns of the water column, because that's the penetration depth of the infrared, photons in the infrared range. So infrared, I like infrared skin temperature measurements a lot, skin velocity measurements a lot. Thank you, great questions.
Yeah, yes, Brennan, can you come here? In front of Nathan's camera.
Ah, yes.
Hey Nate, that was a great talk, thanks.
Thank you very much.
Could you go back about just before the last section?
Uh-oh. I'm getting a specific question.
No, you're getting one more.
One more. So the spectrogram? Or
There.
the growth or the spectrogram?
Nope, there. So
Okay.
you commented specifically on the growth that's happening during and after the rain, but there's something equally strong going on before the rain. And so why do you think the one is significantly more important than the other? Because you've got two sort of pulses of growth going on, and it's not clear why.
So there is rain there, and I think if we had hindsight's 2020, spend $5,000, get a laser discrometer, and actually count the raindrops that are falling, and not just have this kind of standard $10 ticking bucket, we probably would have sensed, because as I demonstrated, but as I showed, the rain really starts here. But it's drip, 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 and because this is a growth rate, you know, there is growth here, but because it's subsiding back down to zero doesn't mean that it's decayed. It's just maybe slowed down its growth and then jumping and then jumping. And so I think what is happening is the rain surface energy in this regime. Let me take a little step back. This right here is the suppression that results from unwinding all of this growth. So I think this is kind of the wind up and then this is the release. And for people who are on Zoom, I'm saying that this is rain. It's not a lot. It's not really that impulsive, but basically there's a lot of growth that's happening in these multiple monitors. Okay, so for people who are watching remotely, the time between 257 and 303, there's a lot of accumulated growth in the gravity capillary regime that's happening there. And then my claim is that at 307, you get this unwinding, where the surface gravity capillary waves subside, they relax, because there's nothing that's kicking them, the rain. And because of the wind forcing, you have no more of this wet blanket effect, where the rain is knocking down the steam, and you get this growth in the decimeter and meter scale waves.
So just
And Dr. Drennan has a follow-up
just
question.
to follow up. So a tipping bucket on a ship is a hard way to measure rain. You get spray, you get drips. So how would you do it better next time? And do you think it's a reasonable measurement now?
Right. So I guess to quote the great Henry Potter, I would say that I'm very confident in my results. He was asked once, "How confident are you in your results?" So I'm very confident. I guess what I would say is I do think it tells us something, which may be meaningless to you. If I were to do it again, I would buy a discrometer that doesn't have those problems, where you actually have a sheet of light, and then it's able to count every time something that causes refraction each time. And so you get not only a droplet distribution, you not only get the total rain rate, you get a droplet distribution in terms of size, and you get a velocity distribution. So I think it's a fantastic instrument, and I would have put it on there. I think I would be very, very nervous about doing analysis of rain impact on the wave field if the rain rate were like 10 millimeters an hour, 20 millimeters an hour. I think what matters, I'm not making a comment that, okay, there's a distinction between 50 millimeters an hour and 100. This was such an enormous rainstorm that you could have measured it with a person holding a bucket. I mean, it was just like, you couldn't ignore it. And because it's such an enormous signal, I think that the tipping bucket isn't ideal, but it tells us, okay, the rain is here, and now the rain's gone. I don't have the video in this presentation, but we had a X-band marine radar running, and it shows the front coming on. It's a beautiful video. It shows the front coming on. It shows this basically where the ship is actually not moved, but the storm has moved to the point where there's this tiny little patch of calmness, and you can see it in the backscatter because you can actually see the surface again. The radar is no longer being primarily scattered by the rain. So that's probably an excellent, I guess, to final answer to your question, I don't really care so much about the absolute accuracy, more the binary. Is there rain, is there not rain? But as you mentioned, there's some gray area in the front end. And if we had a more sophisticated measurement device, we'd be able to make connection on that earlier part, from like 257 to 303.
Thank you.
Yeah, you're welcome. Great questions.
Okay, any more questions from the room? Yes, Milan Churchic, come up to the camera.
Thank you, Danny, for the great talk. My question is, due to hydrodynamic modulation, short waves can, in presence of long waves or absence of long waves, have different properties on average. Does your analysis framework, can it tackle this in any way? Can we use it to learn more about average properties of short waves in different long wave conditions?
I think so. I don't know if that was an intentional 2-inch putt because we wrote a paper on this topic in 2017, but
Related.
okay. Okay. No, that's a fantastic question. I think it's difficult to do it on a ship because
No, go in front of your camera.
it's difficult to do this on a ship because you're bobbing around, and so you're no longer measuring one phase of the wave, right? So you make a measurement. Okay, you're pitched down a little bit. You're making a measurement in the crest, and that wave is moving on you, and then you pitch up a little bit. You can motion correct for a scale, but now you're measuring the trough of another wave, so you can't say anything about, you can't do any kind of like phase coherent averaging or phase conditional averaging.
But how about from the quadcopter?
I think so, yes. So I think you can do it on ASIC, the Air Interaction Tower. I think you can do it on the quadcopter, yes. The quadcopter is challenging just because it's going to, even with the gimbal, if there's an active gimbal stabilization, it does move around a little bit. And it's got real-time kinematics, it's got all the bells and whistles, but it still moves around. And so you have to be really good with motion correction. One nice thing is, we can play around with basically tracking the dominant waves and then referencing all of our spectra to the waves. So assuming if you're in a coastal region and you have the swell system that's coming through, you can get most of the way with the motion correction and maybe do some sort of like wave tracking algorithm where you're following the spectrum along a particular phase of a wave. I think that would be a really powerful way to go after what you're talking about.
I think so. I have just a quick question about this. So considering this was a very strong rain event and it's kind of a small scale and moving transient event, do you think there is some uncertainty about the very long waves being non-local, coming in from elsewhere into your field of view, and maybe that affecting the data itself?
Absolutely. So I think the best illustration of what you're talking about is this, where I report the surface slope variance for waves longer than 1 meter. And the concern could be, well, what if there was a storm that was 3 kilometers away and it gave us the swell? It just happened to coincide with this event. How could we possibly pick that apart? The answer that I give is the mean square slope contribution from those waves, the surface slope variance contribution from waves of those scales are so small to the point where if it's really the 1 to 10 meter waves that are giving the dominant surface gravity wave contribution to mean square slope, and those are much more likely to be generated, if not perfectly locally, I would say they're not from some totally different system where I'm mixing up generation mechanisms.
Right. Basically, the uncertain ones matter less.
That is my argument. And I guess what you could say is, well, these 15 different things are all small, but when you add them together, are they enough to overpower your principal result? It's possible. And I don't love that it was a single event, but as we know with observational science, it's like fishing. You can put a good lure on your line, but sometimes the fish just don't bite. They were out there for 6 weeks and they got one of these.
That's right.
In the southern equatorial Pacific, one rain event. It's almost like magic. It does not happen, I don't think.
Thanks a lot.
Come to Miami next time.
Yeah, next time we'll come to Miami. We'll just go outside at 2 in the afternoon and.
Okay, do we have any further questions? Yes, Payson Tan, come here.
He's not asking.
I am asking. I guess compared to Milan and Will, my question is more of a general one. So I know that the rain impact on the wave is done equatorial Pacific, and I know the heat and salinity will definitely play a part in those waves and momentum transport. So I was just wondering if you or any other researchers have ever considered of rainfalls probably in a freshwater lake, like Lake Michigan, where they have similar wind waves and some extreme events. Well, what do you think the difference will be in between freshwater and saltwater?
Yeah, okay, so I think people heard that because Payson was close to the microphone. In terms of salinity and heat impacting these kinematic properties of surface waves, my intuition is that to first order, the biggest difference would be on atmospheric stability. So in the southern equatorial Pacific, we're talking about, I mean, I can show you the Mononoke line, everything is unstable. You've got the ocean surface that is 32 degrees centigrade and the air is a degree or two cooler all the time. So it's just very unstable, and you have a nice big old boundary layer. Really robust air-sea interaction. I think in Lake Michigan, depending on what time of year you were there, you might have water that's ice, I mean, Brian could talk about this more than I could, but water that's essentially ice cold and warm air, really stable condition. And, you know, questions about whether you're making your flux measurement in the boundary layer, I mean, my intuition is the atmospheric stability is the big part of that. I don't know what, I mean, perhaps salinity and temperature could impact the rheology, so like the material properties of the water. I think that that's going to be more significant with the biogenic films, the gels and things like that. But I think to first order, I mean, there's a reason why the Donlin and Drennan's freshwater measurements hold up in the ocean to first order, I guess, because most of the properties are probably relatable. And maybe it's the details that change when you alter the salinity. Obviously, in high winds, everything's, you know, bubble formation and spray formation is different, but in these kind of calm, you know, 10 meter per second and lower, I don't think it makes a huge difference. But good question. For momentum flux, sorry, for air-sea momentum flux. I'm not saying anything about gas or heat.
Okay, was that all from the room? I think yes. Any questions or comments from our remaining Zoom audience?
There is a chat.
No, the chat, that was just a question.
What was
to
the
repeat
question?
Yeah, that was for Lisa's first question,
Yeah,
but
that
you
was
can
my
repeat
mistake.
it the next one. Yeah, so it looks as if I brought all my speakers here for no good reason today. Anyway, thank you, Nathan, for the presentation. Thank you all for coming. The next seminar will be on Wednesday. We have a 1-hour student seminar. I'm still waiting for the abstract, so watch the emails. Yeah, so that's it for today. Take another donut when you leave. And I hope to see you again on Wednesday.